To film an object traveling at a constant velocity, I rolled a cylindrical makeup container traveling across my dorm floor. Here's a photo of my system. The cylindrical container is rolling from right to left in the negative x direction. The two orange arrows emerging from the camera lens indicate the length of the frame. I started rolling the object before the frame, so the acceleration of the object, due to my pushing it, is not recorded. Inside the frame, the container is moving with a constant velocity. The length of the frame, from arrow to arrow, is about 35 centimeters. This matches up with my tracker data, but we'll take a look at that data in a minute. Newton's second law is algebraically represented by the following statement. It states that if there is a net force on an object in a particular direction, that object will accelerate in that direction. Newton's second law with zero net force is Newton's first law, sometimes referred to as the law of inertia. It states that if there are no net interactions on a system, then the object will maintain a constant velocity. This is what occurs in my system. Note that just because there are no net interactions, that doesn't mean that there are no interactions. If the object maintains a constant velocity, then the net interactions are zero. Now, in my system, the forces of gravity and friction are at play, but they are so small over the distance of 35 centimeters that they are essentially negligible. Based off of the figure in the upper right section of this drawing, you can see that the net force is zero. Therefore, the quantity F net divided by m times delta t is zero. Finally, that means that your final velocity equals your initial velocity. This is the position versus time graph of the container that Tracker produced. As you can see, the graph is linear, indicating a constant velocity. If the graph was not linear, it would contain curves. I modeled my container's position in VPython. I inputted the initial values of position and velocity as 0 meters and 0.206 meters per second in the negative x direction, respectively. I then had a model produced based off of recomputing the object's updated position and velocity every 0.01 seconds. I graphed these model positions with a graph of the experimental positions taken from Tracker. With the forces of gravity and friction across my dorm floor, there is no way for the object to travel at a truly constant velocity. There is some deceleration happening. This is clearly represented in the graph of the experimental system compared to the graph of the model system. At the time of 1.6 seconds, the graph of the model shows the position of the container as about negative 0.315 meters from the origin. The graph of the experimental position is slightly less than that, about negative 0.28 meters from the origin. This is expected. This is because there is a net force in the opposite direction of the object's motion, and therefore a small deceleration has occurred. According to this, that means that the object should not have traveled as far as the model has, and my results show this. Overall, I'm quite happy with the results of my experiment. My model versus experiment graph only shows a slight difference in the experimental versus model position of the object. Given the friction of the floor due to gravity, my results were quite good.